Here we're going to try another example of a double integral over a general region. Here we have the double integral over the region D of y dA. Now if you were to go to a beginning Calc 2 student and say, well, in Calc 3 we did an integral of y today, they would probably not be all that impressed. And then you actually see it unfold and you realize that the integration part is not really the hard part. The hard part comes from this stuff over here. What is the actual region? Well, D is the triangular region with vertices 0, 0, 1, 1, and 4, 0. So, as I recommended in our last video, I'm going to say let's start by actually sketching the region in question. So sketching the region in question, we have 0, 0 as one of our vertices, we have 1, 1 as one of our vertices, and then we have 4, 0 as the last vertex. So the triangular region is going to consist of these three line segments right here. Now we also need to come up with equations for the lines that actually define this region. Now, I would like to point out that we could go type 1, we could go type 2 with this, but if we were to go type 1 with it, I do need to point out that our top function does change in here. So if we're going to go type 1, we would actually have to set up two double integrals to evaluate this. Now we are going to do that because, well, it's the weekend and I don't have a whole lot of other stuff to do, so it's all good. We'll actually start with type 2 though. For type 2, going from left to right, there's only one left function and there's only one right function. We still need to come up with what they are though. We need to bound x between these functions of y. Now, as far as the line connecting 0, 0 with 1, 1, I'm just going to go ahead and label these three line segments as 1, 2, and 3. 1 is going to be fairly straightforward to figure out. That is the line y is equal to x. As far as line 2 is concerned, if you're connecting two things along the x-axis, that's definitely going to be the line y equals 0. Now for line segment 3, my recommendation would be to go with y equals mx plus b. So going with y equals mx plus b, we're going to have a slope of, let's see, going from this point down to this point, y goes down by 1, and x increases by 3, going from 1 to 4. So that'll be negative 1/3 x plus. If we were to continue this line backward to the y-axis, it would increase by another 1/3 as x changes by 1, as is indicated by the slope. It was at y equals 1, it goes up by 1/3, that would be 4/3. However, if we want this as a type 2 region, we would need to express this with x as a function of y. We can do so by multiplying both sides by 3, adding x to both sides, and subtracting 3y from both sides. So this would be as if you were considering that for every 1 that y decreases, x is increasing by 3 for a slope of negative 3. Now the left function would be x is equal to y. The right function would be this other slanty line, so negative 3y plus 4. And then y, if we're going to bound that between two constants, is going to go from 0 all the way up to y equals 1. So those are the bounds for our type 2 double integral. Let's go ahead and put that together. So the double integral over the region D of y dA is going to be equal to, first integral will be with respect to x, and the second one will be with respect to y. So with respect to y, we'll go from 0 to 1, and with respect to x, we'll go from y to negative 3y plus 4. And to reiterate, we're going with respect to x first, then with respect to y. That way, this corresponds to this, and this corresponds to this. So, evaluating this integral with respect to x, y would be treated as a constant. Therefore, this is going to be equal to y times x, as x goes from y to negative 3y plus 4. So, plugging in each of those bounds, we are going to get y times negative 3y plus 4 minus y times the lower bound of y. We can simplify this using a little bit of algebra, the distributive property specifically. This will be negative 3y squared plus 4y minus y squared dy. Go ahead and combine those like terms, and we will have negative 4y squared plus 4y as y goes from 0 to 1. This looks like it's now ready to be integrated, so we will go ahead and do so. So negative 4/3 y cubed plus 2y squared, going from 0 to 1. Plugging in 1 will just give us the coefficients of this polynomial, so negative 4/3 plus 2. And plugging in 0 will give us a lot of 0. Final answer for this one, evaluated as a type 2 double integral, will be 2/3. Now I did mention I did want to try this as a union of type 1 regions as well. So I'm going to recopy this triangle on the other side of the page, and we'll set this up as a union of 2 type 1 regions. So 0, 0, connect to 1, 1, connect out to 4, 0. Now because the top function changes, that's why we're going to need 2 type 1 regions. Good news is we came up with the equations of all of these on the previous page. So for region number 1, we need to bound y between 2 functions. You'll notice that the lower bound is the x-axis, that would be y equals 0, and the upper bound was that line y equals x that we had from earlier. And x is simply going to go from x equals 0 to x equals 1. Now for the second region, in the second region the top function would be this slanty line here. And the bottom function would once again be the x-axis. So x-axis is y equals 0. And this line we got on the previous page, that was negative 1/3 x plus 4/3. Now x for this region starts at x equals 1 and extends all the way down to x equals 4. So if we are going to go type 1 with this, we do need 2 double integrals. And this will look like the following. Double integral over d of y dA will be equal to, for the first integral, that'll be from 0 to 1, and from 0 to x of y dy dx. That way this corresponds to this, and this corresponds to this. Plus, for our second region, which I realize I never labeled, that would be using this over here. So with respect to x, that'll be from 1 to 4, and with respect to y, that'll be from 0 to negative 1/3 x plus 4/3. Once again, this will be y dy dx. And make sure that we know what corresponds to y. Good. So, as far as type 1 is concerned, this is probably not ideal because you do have 2 double integrals to evaluate. Good news is this first one should go relatively quickly. So we'll do this one over here. Integrating with respect to y, we will get 1/2 y squared, going from y equals 0 to y equals x. Plugging in our upper bound will give us 1/2 x squared, and plugging in the lower bound will give us half of 0 squared. This is, of course, a fancy way of just saying 1/2 x squared dx. Evaluating this using the power rule should be no problem whatsoever. We'll call this 1/6 x cubed, going from 0 to 1. So final answer for this portion will be 1/6. Now, that is not the same as the final answer we saw on the previous page because we need to add to that this result over here. So, once again, let's go ahead and evaluate this integral first with respect to y. This will be 1/2 y squared, going from lower bound 0 to upper bound negative 1/3 x plus 4/3. And now all of a sudden my happy feeling is gone as I realize I have to square that. Let's pull the 1/2 outside of the integral and say that this will be negative 1/3 x plus 4/3 quantity squared minus 0 squared. That is once again upper bound minus lower bound. And then expanding this so that we can make use of the power rule, this will be 1/9 x squared minus, multiply that times that and double it, 8/9 x plus 16/9. Oh yes, happy feeling is definitely gone as we, oh boy, integrate and then plug in no bounds of 0. Well, nobody said that doing Calc 3 was going to be glamorous all the time. Bummer for us, undoubtedly. So evaluating each of these according to the power rule, we'll get 1/27 x cubed minus 4/9 x squared plus 16/9 times x. Now, I'm going to go ahead and take the liberty of showing you what this will look like and then grabbing my calculator to actually perform all of this. I'm not saying that I couldn't do it in my head. What I'm saying is it's like 8:30 a.m. on a Saturday, and I'm just, I'm still waking up. 1 squared plus 16/9 times 1. All right. Now, I'm fairly certain that our final answer for all of this is simply going to be 1/2 based on the results from the previous page. But, well, let's go ahead and cross our fingers. So I'm going to start with all of the stuff that's inside the parentheses here. So we'll do 1/27 times 4 cubed minus 4/9 times 4 squared plus 16/9 times 4 minus, when I plug in 1 for all of these, it's just going to be whatever the coefficients are, so that'll be 1/27 minus 4/9 plus 16/9, and I'll throw that in parentheses so that this minus sign will distribute to all of them. Fingers definitely crossed on this one. I'm hoping that this is all just going to be 1. Oh yeah, it's 1. Good, because then we multiply that by 1/2. Good Lord, I just used my calculator to multiply 1 times 1/2. I'm just going to go ahead and put that away. Let's never speak of this again. It's not like somebody's recording this. Oh, shh. So all of this is equal to 1/2. Now, as a reminder, what we got from region 1 was 1/6, and what we got from region 2 was 1/2. So final answer would be 1/6 plus 1/2. Get a common denominator for those and add them together, you'll get 4/6, which reduces down to 2/3. So please be aware that you only need to set this up as either type 1 or type 2. You're not required to do both. And hopefully this demonstrates that sometimes making a selection that is type 2 or type 1 can be really advantageous so that you don't have to do, you know, this. That was kind of gross. Still glad we did it though.